All right. Welcome, everyone. Thank you for joining us on this wonderful Monday. In today's presentation, we will be introducing Constellation. Constellation is an open source, serverless end-to-end framework that simplifies the challenges of geographically distributed API load testing. First, I'd like to introduce the Constellation team: Andrew, Jake, Jason, and myself, Stephen. Unfortunately, Jason is ill, so Jake will be filling in for him today. Otherwise, you'll hear from each of us throughout the presentation. We'll start with exploring the problem space that inspired Constellation, see where Constellation fits in the solution space, talk about its engineering design and architecture decisions, and lastly, discuss some of the challenges and future work. We'll start off with what load testing is in order to better understand Constellation's problem space. Load testing measures how a software program reacts to multiple concurrent users' requests. A load in this context is a set of requests made over a period of time to any program that handles requests. These can be websites, web apps, or APIs. The illustration shows that virtual users represent real users in making requests to an API endpoint. So, why is load testing important for developers? Load testing is important because it helps to confirm system performance assumptions by getting insights like the maximum amount of users the API can handle, the effect of traffic on response times, and number of successful versus failed requests. As an example, say Amazon has 3 million customers trying to make purchases simultaneously on Black Friday. The developers want to ensure that the service can handle that amount of traffic ahead of time. The developers do not want to discover that the system cannot perform as expected on Black Friday. Amazon found that every 100 millisecond delay in page load costs 1% of sales. As of 2021, this 1% of lost sales revenue would be approximately $3.8 billion. And a page's load and response times can suffer under a high load if users are located further from the servers and the servers are not optimized to handle such a large volume of requests. What about manually load testing? Manually mimicking 3 million users accessing Amazon would be time-consuming and expensive. A single person or multiple people without test automation tools could not replicate this load. Let's look at two load testing approaches, browser-based and protocol-based, that address this challenge. Browser-based load testing simulates web traffic with virtual users following a script on how to interact with application elements in actual browser instances. The goal is to simulate actual user behavior, flows, or transactions in an application. An example would be a user logging into Amazon and going through the checkout process for a purchase. Protocol-based load testing, on the other hand, simulates loads to servers using the underlying network protocol without a browser. An example is virtual users sending HTTP requests to Amazon without using a browser and then measuring the website response. We chose to focus on protocol-based load testing for the following reasons. Test scenarios can be run without the need to develop a user interface. It is less resource intensive in terms of CPU and memory usage because no browser needs to be launched. This means you can generate more virtual users with the same amount of resources. And the most suitable use case is for explicitly testing APIs. Developers can encounter many challenges in developing APIs. As APIs integrate with more services and get increasingly complex, it can become difficult to determine where performance degradation occurs and what areas to optimize. The location of consumers can also affect API performance. In an ideal situation, two consumers anywhere in the world would experience similar performances. Constructing the infrastructure to test that is a non-trivial problem. If we look at the picture here, the API provider is located in Europe. One consumer is located in South America and has a response time of 100 milliseconds. And another consumer located in Australia has a response time of 225 milliseconds. In this case, developers must investigate why these regions are experiencing service differences. This form of load testing, where the load is generated from distinct geographic locations, is called geo-distributed load testing. Many open source load testing applications exist but are challenging to use synchronously in different geographic regions. That capability, geo-distributed load generation, is usually in the premium version of their open source tool. These premium cloud-based solutions include Artillery Scale, BlazeMeter, and K6 Cloud. While developers can easily leverage these tools to perform load testing, they must consider the service limit trade-offs. Looking at the table, we can see that there are limits on the number of virtual users, test duration, and data retention. We built Constellation, which addresses some of these limitations. Let's look at each of the headings next. Virtual users. There are different tiers for each of the premium cloud-based load testing solutions. The number of virtual users is limited by the subscription tier selected. Virtual user limits can be increased by upgrading the subscription tier. With max test duration, having a maximum test duration with no limit is essential if developers want to test a system over several hours to validate system behaviors and uncover bugs and reliability issues. Again, looking at the table, Constellation and Artillery Scale have no limits on the max test duration, while K6 Cloud and BlazeMeter are limited to 1 and 2 hours. Again, you can get a longer max test duration by upgrading your subscription tier. Data retention. The cloud-based SaaS solutions retain data on a rolling subscription basis. Once a subscription ends, however, the data is automatically deleted, or there may be an option to purchase data retention. Constellation's data retention period is 12 months, AWS's maximum period. This means Constellation can keep data for an extended period without paying a monthly subscription outside of the AWS fees. In comparing Constellation with the existing cloud solutions in terms of features, Constellation is limited to HTTP requests, parallel testing with a single test script, and the visualizer displays limited metrics without further analysis. Constellation is for developers who need a flexible, scalable, open source solution where cloud-based tiered SaaS solutions are too restrictive, excessive, or costly. Next, I'll hand it over to Andrew, who will talk more about Constellation and its design decisions.
Thanks, Stephen. First, I want to give you a quick overview of the Constellation infrastructure. The framework is run from the command line, given a couple of user-generated setup files. Constellation then uses this information to deploy several cloud components using AWS services. These components are split into home and remote regions that the user identifies. The home region is where they want to store the data, and the remote regions are where they want load to come from during their load test. Jake will discuss these files and components in more detail later in the presentation. But before we get too far into Constellation's architecture, there were several design decisions we needed to make prior to and during development of Constellation, and we'll walk through a few of them now. First, we had to decide how we were going to perform the testing itself. Given an API to test, there are two main testing approaches, usually referred to as non-scripted and scripted. Non-scripted testing is relatively simple. The test hits a single target endpoint with requests in a given time frame, typically measured as requests per second. The results are relatively straightforward. It shows how performance varies given a strictly defined load on an endpoint. What happens to the system with 1,000 requests per second or 100,000 requests per second, and so on. While this can be useful for finding some performance issues, these tests don't typically simulate real-world use very well. Overloading an endpoint could affect the performance of another endpoint for a variety of reasons, such as it being a direct prerequisite to its use or consuming shared resources. Scripted tests, on the other hand, test an API as part of a defined workflow. A virtual user performs some scripted operations. For example, it may make requests to log in, fetch user data, make some database changes, and finally log out. These requests can have pauses in between or be made simultaneously, whatever most accurately represents how a user will interact with the API. The test load is then scaled by adjusting the number of concurrent virtual users. What happens with 1,000 concurrent users, 100,000 concurrent users, etc. However, setting up a scripted test is a much more involved endeavor. Developing the framework for simulating a user requires a significant effort in order to avoid restrictive resource requirements. Because while 10,000 users may be using 10,000 devices in the real world, we'd rather not have to requisition that much hardware in order to perform a test. Additionally, developing the test itself, how many users will perform what actions, requires a clear understanding of the API's use case. And it's very easy to perform a test that doesn't accurately represent how a user will actually consume the API. Despite this increased complexity, we decided to use the virtual user scripted strategy for Constellation. Scripted testing is just a significantly more realistic way to test an API as a whole, and this allows Constellation to accurately simulate users consuming an API simultaneously from around the world. Once we decided to use virtual users, the next question was, how do we implement them? A VU must simulate a user as closely as possible, while still operating as efficiently as possible. The less resources it takes to simulate a single user, the more VUs can be generated with the same infrastructure. The VUs should also be independent from each other. If one VU encounters an error or has poor performance, it shouldn't impact any of the other VUs, which requires some amount of parallel processing. We wanted to build the load generation tool using JavaScript, and there are several ways we could go about simulating users in Node.js, including promises, child processes, and worker threads. We evaluated these options by looking at their ability to perform concurrent processing, if they were limited in quantity, the processing overhead of running them, and how optimized they were for input-output tasks, such as making HTTP requests. Node.js worker threads enable parallel JavaScript threads within a single node process. We disregarded them early on because they are primarily a way to take advantage of multi-core processors for concurrent CPU-intensive tasks, like, say, some calculation that takes 10 seconds to complete. They are limited by the number of cores in the hardware because each thread is meant to be processing simultaneously. Child processes, on the other hand, generate separate Node.js processes, which is an excellent simulation of individual users. Each virtual user would operate independently of any other virtual user. However, child processes have a significant performance overhead, as each process has provisioned memory and depends on the CPU's process management. Node.js promises don't allow for concurrent processing, but they are optimized for concurrent idling. 5 HTTP requests will be done one at a time, and the responses will be processed one at a time on a first-come, first-served basis. But the waiting period between the requests and the responses is done simultaneously, and the number of promises is only limited by the amount of memory available. Ultimately, we decided to use promises. This does mean that 2 requests can't be sent at precisely the same time, but they will be executed within a few CPU cycles of each other, which is sufficient for load testing because latency differences would most likely prevent them from reaching the endpoint at the same time anyways. The last major design decision that we'll discuss today was the question of what data do we store? Load testing services can generate a huge amount of data. They are generating a large number of requests and store some details for each response that is received. The responses can vary from a simple 200 OK to a large content download. Even when only storing metrics, like the response's size and status code, the sheer number of them can be daunting, easily in the order of millions. Because load testing tools generate so much data, the tool can be seen conceptually as a large data pipeline. And there are 2 common approaches to managing a data pipeline, ETL and ELT. These acronyms define the order in which 3 processes occur: extract, which is collecting raw data from a data source; transform, processing and converting that raw data into a usable form; and load, putting the transformed data into the target system. The difference between ETL and ELT is, when does transformation take place? An ETL pipeline will transform the data prior to loading it into the target, resulting in a longer loading process and a faster analysis after the data transfer is complete. As a result, raw data is lost and only the transformed data is stored. If you need a different transformation later, you need to reacquire the raw data. An ELT pipeline loads the data directly into the target, and the target system performs any transformations it requires. This allows transformation to be performed as needed on subsets of data and for different transformations to be performed at any time. However, this usually increases the total data loaded into the target. We took the ELT approach for Constellation's primary data pipeline from the load generation service to the database. This means that the complete data set is then available for inspection by the user, either using the built-in Constellation visualizer or using other third-party software to query the database. While this results in much more data being stored in the database, it allows users to access the data directly and perform any transformations they need on Constellation test results without any loss of data or processing delays from a generic transformation process. Now, I'll pass things along to Jake for a look into Constellation's final architecture.
Thanks, Andrew. Now that we've talked a little bit about why load testing is a problem that needs a solution, and about some of the design decisions that we made along the way while developing Constellation, I want to now talk a little bit about the internals of Constellation and what actually goes into a geo-distributed load testing application. Constellation is a service that is installed on a user's local machine and uses the cloud in order to enable distributed testing. The Constellation cloud architecture includes a home region and some number of remote regions. Each piece of Constellation's architecture is made up of multiple components that make testing possible. Each part of Constellation's architecture holds one or more of the following components: the CLI, load generator, data aggregator, and visualizer. And I'm going to go more in depth with both the architecture and the components in later slides. Every test will start with some sort of user input, so we'll start by taking a look at the CLI. Interacting with the Constellation framework requires the locally installed CLI application in two user-generated files: the configuration file and the test script file. More specifically, the configuration file is used to determine the number of VUs and the number of regions the infrastructure needs to accommodate. The test script is responsible for the details of the user behavior to simulate and is uploaded to an S3 bucket to be later used by the load generators. Once the test has created the configuration file and the test script, the user can then initialize infrastructure and execute the test accordingly. Let's now draw our attention to the home region, where the first step of the testing process begins. The home region acts as a hub that sits in between the user's local system and the remote regions, containing orchestration and data storage. Using the configuration file to initialize the remote architecture and receiving the test script to be sent to the remote regions. Finally, returning any testing data from the remote regions to a timestream database in the home region. Once the initial setup is complete, the focus moves to the remote regions and generating the actual test load. Each remote region hosts some number of load generation containers, depending on the desired number of VUs. Each load generator is limited to 200 VUs to provide flexibility for test scripts. The load generators retrieve the test script and configuration from the home region. The load generator fulfills Constellation's needs to simulate VUs that repeatedly execute the user-defined script, generating requests and passing the resulting metrics to the data aggregation container. Drawing attention to the diagram, the API call that retrieves the test script is represented by the spinning arrows on the left, and the load generator itself is represented by the person in the very middle of the diagram. While on the right, we see an example of what the resulting test object looks like after a single run of the test script. This object contains the start time and runtime for the test script, as well as the start time, latency, and other defining characteristics of the HTTP calls made during that run. These test record objects are sent to the data aggregator in batches every 10 seconds. Once the test duration ends, Constellation sends a final batch of tests to the data aggregator. Next, I'm going to be talking a little bit about why the data aggregator is so important and what its function is in each remote region and the load generation process. In addition to the load generators, each remote region hosts only one data aggregator that receives data from each load generator in their respective remote regions. As each regional load generator sends its completed test results to the data aggregator, they are saved in a SQLite database that acts as a temporary data store that we will name the cache. The aggregator has a single route that is responsible for parsing and formatting the incoming data from the load generators and saving the data to the cache. The aggregator then writes the data from the cache to the time stream database in 10-second intervals. The aggregator is also responsible for utilizing TimeStream's ability to handle batch write requests of 100 records per write and handles AWS throttling exceptions to achieve more efficient write speeds. At the end of the test, the aggregator continues attempting to send data to TimeStream until it stops receiving data. After the data from the aggregators has been written to the TimeStream database, the data can then be accessed by the Visualizer app as the very last stop of its journey. Let's now take a look at what the data from a test will look like once testing is complete and the data is being visualized. For reference, the graphs in the next series of short videos is showing the data for a test that ran for a total of 10 minutes, testing 2 different API endpoints from 5 different regions. The data visualizer defaults to the consolidated regional latency graph, which is the long way of saying that we can see the average latencies of every region we have tested in one place being aggregated by the same amount of time. Now, this is quite a lot of data points. Let's talk next about how we can clean this data up and what we're already doing to make the data look a bit cleaner. The first thing I want to mention that's going on in this GIF is the exclude first 2% button at the top right corner of the screen. We noticed during testing that no matter what API we were testing, there's a large latency spike at the very beginning that wasn't representative of the rest of the data. We decided to place this button in the UI because it allows the user to gain a more useful perspective on the test data without deleting any potentially useful data in the process. In addition to this button, the user can choose to see their data aggregated by either a 1, 5, or 10-second interval. This feature becomes invaluable the longer that the test is run for. The Visualizer app also allows the user to see only one region at a time by selecting which region you would like to view using the dropdown. We can also see the ratio of success to errors in an easy-to-read bar graph next to the regional test latency graph. Finally, you can also choose to see the graphs for individual regions all in one place with the All option in the regions dropdown. So far, we have gone over the components that make up Constellation, as well as Constellation's architecture, starting from the local system, moving into the cloud, and finishing with the data being visualized back in the local system. Next, we're going to dive into some challenges that we faced when developing Constellation and what we have done to overcome them. The Constellation framework allows the user to test an API with virtual users that are coming from one or more regions. From the perspective of the infrastructure, the amount of virtual users in a test dictates the number of components involved in creating the infrastructure. In addition to this, the regions chosen by the user dictate how these components are distributed. While developing Constellation, handling this manner of distribution presented significant challenges. In this section, I will be highlighting a couple of more interesting challenges and the solutions we came up with to tackle them. The first challenge is minimizing deployment time. The framework allows testing from as many regions as AWS provides. As such, up to 23 regions can be involved for a single test. Before trying to optimize our deployment strategy for speed, our initial approach was synchronized deployment. This involved waiting for one region to finish deployment before starting another. The diagram illustrates the manner of deployment for 3 regions using this strategy. During development, we have found that each region takes around 5 minutes to deploy. If 23 regions are used, a user will have to wait up to 2 hours before their test even executes. This is clearly far too long. For our solution, we implemented a parallel deployment strategy. Here, we managed to isolate each regional deployment as a singular process, which is then executed in parallel. Because all regions start deployment at exactly the same time, the user will only have to wait for a limited amount of time before the test is run. The wait time now becomes just as long as the slowest region will take to deploy. As such, a user will only have to wait for around 5 minutes, no matter how many regions they chose to involve in a test. The second challenge I would like to highlight is test synchronization. During development, we have found that only 200 VUs can be generated by a single load generating component due to memory and CPU resource limitations. Since Constellation allows simulation of up to 10,000 VUs, the responsibility of load generation must be distributed to multiple components. However, distributing work into multiple components presents its own challenges. If multiple components are involved, they will execute their load generation at different points in time. This means that the overall load generation is staggered. From the perspective of the API being tested, staggered load generation means that it will not experience all 600 VUs at the same time. As such, the measured performance for that API will not be accurate. The issue then is how to synchronize components so that load generation happens at the same time, despite being a distributed responsibility. Furthermore, our architecture demands the existence of an additional component in our remote regions, the data aggregator. This component receives data from the load generators for further processing. In the diagram, we illustrate a load generator sending data to an aggregator that's still getting ready. Since the data is not ready to be received, it is dropped. As load generators and data aggregators are separate components, this could happen without proper synchronization. In summary, the need for synchronization comes from 1, the need to prevent data loss resulting from sending data to an aggregator which is not ready to receive data, and 2, the need to have all load generators execute at the same time. In order to tackle the problem of test synchronization, we introduced an additional component, the orchestrator. This component is essentially a central lambda responsible for interfacing with the distributed components to achieve test synchronization. The diagram here illustrates where the orchestrator sits relative to other components already presented. To illustrate the job of the orchestrator, we decided to lay out 3 scenarios of increasing complexity. The first is a single region with a single load generator. The second is a single region with multiple load generators. And the third and final scenario involves multiple regions. This last scenario is precisely the kind of geo-distributed load testing that Constellation facilitates. In the first scenario, we have a single load generator and a single data aggregator. The requirement here is that the load generator should only undertake load generation once a data aggregator is ready. To illustrate how synchronization would work, let's draw our attention to the diagram with the 3 main components in this process shown. The first component is a violet bar, which represents the data aggregator. The second component is the load generator. This has an orange bar representing the actual VU simulation, and a gray bar, which is not a component, but represents the blocking process. The third and final component is the orchestrator to the left. In this example, the load generator is ready first, but the blocking process prevents the load generator from beginning early. In essence, this blocking process continually pulls the orchestrator, waiting to receive a signal if the load generation should begin. From the perspective of the orchestrator, it will keep the blocking process going until a ready signal from the data aggregator is received. Overall, we can see that this has an effect of guaranteeing that an aggregator is ready before any load generators begin sending data. In this second scenario, we now have multiple load generators. One requirement here is that the load generator should only execute once a data aggregator is ready. Another requirement is that all load generation should start at the same time across the distributed components. To aid in demonstrating how synchronization would work in this scenario, we represented it in the following diagram. Here we see 3 load generating components, which are ready at different points in time, but load generation is prevented from starting early. This blocking process eventually receives a time to execute, or TTE. This is represented as a watch in the diagram. In essence, this indicates the point in time in which load generation starts. From the perspective of the orchestrator, the TTE is only calculated when it receives a ready signal from the aggregator. At a high level, since all load generators receive the same TTE, VU simulation is synchronized. In the diagram, this is illustrated by the 3 orange bars being perfectly lined up against one another. In this third and final scenario, we now have multiple regions, which is most reflective of what Constellation facilitates. Here, each region contains a local aggregator accompanied by multiple load generators. The first requirement here is that all load generation must start at the same time for all components, independent of region. The second requirement is that the respective data aggregators are listening before any data is sent to them. In this example, we illustrate 3 regions with 1 load generator each. We again see that the load generating components start at different points in time. And just like before, the blocking process halts any load generation from starting early. For this scenario, the calculation of the TTE is slightly different. Turning our attention to the top left-hand side of the diagram, we can see that the orchestrator knows which regions to expect ready signals to come from. As the local aggregators from the 3 regions become ready, their respective signals are sent and received by the orchestrator. Once all expected ready signals are received, only then is the TTE calculated, which is then passed on to load generators. Overall, this has the effect that all load generators across regions execute at the same time, while also guaranteeing that aggregators are readily available to receive data. At a high level, this is how the Constellation framework achieves the requirements of test synchronization, thereby ensuring accuracy and preventing data loss, despite working with components spread across the globe. Of course, software is never done, and we have several ideas for improving and expanding Constellation. As stated earlier, currently all of the test results are stored in the database. While we prefer this approach as the default, not all of this data is useful for all users. We'd like to give users the option to perform some data transformation before storing the data if they would like to. Additionally, both the load generator and data aggregator would benefit from being implemented in a more efficient language, such as Go, to improve performance, which would increase the number of views a single instance can produce. And with that, the rest of the Constellation team and myself would like to thank you for watching our presentation. We'd like to open up the call for any questions you may have about Constellation or our process of development. So Scott says, what did you use for those great diagrams? Oh shoot, I think Jason, that's a question for you.
That's a secret. Sorry, no, we use Excalidraw. Highly recommend it.
And then Juan says, what are your favorite problems to devise a solution for? I can only, speak personally. I worked on the data aggregator. I think my favorite problem was figuring out how to receive data while simultaneously sending it to TimeStream. I know the other group members have a different answer for this question. Actually, we'll pass that one around. Andrew, Jason, Steven, any favorite problems?
It was very interesting looking into the different ways that we could create these virtual users. This is why one of the sections I was presenting on there was just the different options on how to simulate multiple people all attacking an API all at the same time.
Yeah, and as for my section, I worked on the orchestration and the infrastructure, and just making all of the components work across the globe, and trying to even think about that was a really challenge to begin with. And I thought that was an awesome problem to solve, and that's why we dedicated a lot of the presentation for that orchestration bit, because it was a really big challenge.
You got one, Steven?
Mine is similar to Andrew's. I was working with him on the load generator, the concurrent users, creating the virtual users. That was the most interesting problem. Yeah.
Great, thanks guys. And then for Mitch, he says, how did you decide to take on this particular problem? And how did your project change as you delved into the problem space? What's funny is that we were actually looking at observation at first. And then, as we started looking into the problem space a little bit more, I think we all can probably agree, we started losing interest in the problem space. And then Jason might be able to expand on this a little bit, but it's thanks to him that we landed on this issue. It was just a really neat problem to see a load tested across the globe. It's something that we hadn't talked of before, and we all know Jason, at least in our group, that Jason's excitement can rub off on all of us. So I think that's really how we got started.
Thanks, Jake. I appreciate it. Yeah, I mean, at the start of our project, we only looked into stitching together open source projects. But eventually we were convinced that we had the capabilities to build everything ourselves. So we could have used an open source tool for load generation. We could have used an open source tool for data aggregator, but we decided to write everything ourselves, and that's how we kind of like evolved. We evolved by expanding our scope. But overall, we were very proud of what we achieved in this one.
I agree. An anonymous attendee says, really cool project, well done. You managed avoiding data loss by making the service wait until data aggregators are ready. What happens if a data aggregator crashes while transporting data? Would your solution still preserve data? That might be a question for, actually, that'd be a question for me and Jason. Well, I know that, so we built the data aggregator with a SQLite database within the aggregator. So SQLite is an in-file system database. So as it's receiving data, it's constantly writing data to that SQLite database. If this the aggregator would crash, the data would still exist. It would be another question that, how do we retrieve that data? I don't know if Jason have anything to add on that, because I know he's on the architecture side.
So ultimately, the data aggregator is actually a monolithic solution. Andrew, I don't know if you can find a data aggregator slide, but yeah, you have a receiver, you have a cache in the middle, and then you have a sender on the right-hand side. And essentially, this is a monolithic solution. And so the SQLite database is kind of like in memory. Yeah, there it is. I can see it. I believe that if it crashes, it actually loses everything because it's just a container, right? We did think about using a separate service like Amazon DynamoDB for cache, or Redis or RDS, but essentially that's using a separate service to act as a cache that we only need for a very specific amount of time. And so the question here is that, do we keep a monolithic simple solution that's a bit less resilient, or do we build in resiliency by keeping the cache as a separate service and not a SQL database within the same container? But it's a good question. When it crashes, it loses the data.
Joey says, were there any alternatives to orchestration with a Lambda that you considered?
I know that there's some CloudWatch where you can look at events as things are spinning up. I know that they exist, but we didn't have time to kind of like look at other orchestration solutions. But it's another good question. Thanks, Joey.
Another one from Scott. How difficult was utilization of AWS to deploy in these different regions? A lot of problem solving seemed to be around the end solution, but was figuring out that via AWS a hurdle?
Yes, massively. Andrew, if you go to the synchronized deployment part, the parallelized deployment part, so what we used AWS CDK to deploy into different regions. What we initially found is that there were a lot of problems with tackling multi-region deployment. And so I think the way that we kind of like did that is just having a really robust CLI, and that Andrew, I believe the third slide from the last would show them the CLI, and I think that's a good part to show the people here. It has a lot of checks to make sure that the configuration file that the user creates first has a lot of checks to make sure that when it's deploying to different regions, all of your configuration is correct from AWS side. Otherwise, the CLI will just call you out. It will give you instructions on how to fix your deployment before trying on all of these different regions. Yeah, I hope that answers your question.
Okay. Michael says, I like TTE as a solution to synchronizing execution across regions. Very neat. Could you talk about how you guys decided on this and any potential alternatives? Were there any challenges in calculating this?
Oh yeah, yeah, TTE was a really cool bit. Yeah, if we just click the slide to the multi-region deployment synchronization. Yeah, during our first live demo with our mentors, trying to figure out synchronization was a really big challenge. We didn't really have time to look at other potential solutions. Again, we could have done some kind of event-driven programming in this side, but there is some limitations to TTE that we actually didn't talk about. Yeah.
Okay, well, it looks like there's no more questions. With that, I'd like to thank you all again for coming to our presentation. It means a lot to us that you guys came and stayed through the whole thing. And with that, we hope to see you around in the Launch School general chat.